Welcome to the video for problem 2.20 of Engineering 623. This problem, as you can already see, is a Smith chart problem, and so the main features of the Smith chart are shown here, and the discussion of the problem is shown below. Now, the problem actually says the following. It says, use the Smith chart to find the following quantities for the transmission line circuit shown in the accompanying figure. And the quantities that are desired are A, the SWR on the line, B, the reflection coefficient at the load, C, the load admittance, D, the input impedance of the line, E, the distance from the load to the first voltage minimum, and finally F, the distance from the load to the first voltage maximum. So the first thing we do for this problem is to find the normalized load impedance. This is supposed to be a capital Z sub L, and this is supposed to be lowercase z sub L to represent the normalized value of the load impedance. And the normalized value is simply the load impedance divided by the characteristic impedance of the line. And so in this case, the normalized load impedance turns out to be 1.2 plus J1. And so the first thing that we will do with the Smith chart is to plot that point on the Smith chart, and that has been plotted with a red dot. So if you come up here, you can see, remember it was 1.2 plus J1, so you can see the 1.2 and the plus J1, and so you see the red dot here. And that's the first thing that we plot on the Smith chart. Now the next step is to use a compass to draw a circle that goes through this dot and is centered at the center of the Smith chart. Now, to be honest, as you can see, it's not really necessary to draw the circle. But what you do have to do is go ahead and use your compass to determine the length from the center here, which would be the center of the circle, out to the red dot. Because once you have that distance, then you will come down here to the scale at the bottom, and measuring from the center to the left, here you on this first scale you can get SWR, and on the third scale, measuring once again from the center to toward the left, you can get the magnitude of the reflection coefficient. And that is described in a little more detail in number 4. It says, without changing the setting of the compass. In other words, we don't change that radius. We use the same radius for the circle if we had actually drawn the circle, but again, it's not absolutely necessary to draw the circle. But without changing the setting of the compass, use it to measure SWR and magnitude of gamma on the scales under the chart. And if you do that in this case, you will get SWR of 2.45 and magnitude of gamma is 0.422. Then the next step after that is to draw a line through the red dot from the center of the chart to the edge of the Smith chart. And so if we look, we can see that that line has been drawn here from the center of the chart through the red line all the way to the edge of the chart. And we see that now, remember, we've already determined that the magnitude of gamma is 0.422, but now we can get the phase of gamma as 54.5 degrees. And the way that we do that is we look here at this scale for the angle of the reflection coefficient. And I've estimated that to be 54.5 degrees here. Now the next step, we need to know the length of the line, which in this case is 0.4 lambda. So we go 0.4 wavelengths, and we're going toward the generator. So we go in the clockwise direction on the Smith chart. And so let's see what will happen there. Now this original line you can see is at 0.174 lambda. You see 0.17 here and 0.18 here, so this is 0.174. And then we're going to go 0.4 of a wavelength in the clockwise direction. Well, keep in mind that one complete revolution around the Smith chart is 0.5 of a wavelength. So going 0.4 of a wavelength in the clockwise direction is the same as going 1/10 of a wavelength in the counterclockwise direction. So we have 0.174 here, and over here we'll have 0.074. And we will draw another line from that point to the center of the Smith chart. And then we can see, again, by if we still have our compass set at the correct radius, we can measure from the center out along this line, and we can see where that line would hit the that circle. And this will be our normalized input impedance to the transmission line. The red dot is the normalized load impedance. The green dot is the normalized input impedance. And that is summarized down here. Just draw another straight line. See the green dot where this line intersects the circle. I have estimated that to be Zn equals 0.5 plus J 0.5. And if we come up here, I believe you can see where I get that. Here is the J 0.5, and here is 0.5 for the real part. And now keep in mind that's the normalized input impedance, and so to get the unnormalized input impedance, we multiply this by the characteristic impedance of the line, which is 50, and so we get Zn is equal to 25 plus J 25 ohms. And now to answer these questions about the first voltage minimum and first voltage maximum, let's come back up here one more time to the Smith chart. Remember that this line over here corresponds to the what's going on with the load, and then as we start moving toward the generator, in other words, in the clockwise direction, okay, when we get here, we know that that corresponds to a voltage maximum. And when we go all the way over here, that corresponds to a voltage minimum. Now again, all the way around the Smith chart is half of a wavelength, so halfway around is 0.25 wavelengths. And then we have from here, this was 0.174, and this is 0.25, so I guess that's 0.076 plus the quarter is 0.326 lambda. And sure enough, that's where the first minimum will be. But for the first voltage maximum, you just go from this point over to here, so that's 0.076 lambda. And so that that gives you the answer, all the answers. Here's your standing wave ratio is 2.45. The reflection coefficient is 0.422 at an angle of 54.5 degrees. The input admittance is 1 over the input impedance, so that's easy. You don't need the chart for that one. Z, input impedance, we said we got an estimate of 25 plus J, 25 ohms. Distance to the first minimum is 0.326 lambda. Distance to the first maximum, voltage maximum, is 0.076 lambda. And that's how we use the Smith chart to solve problem 220.